The nucleus is composed of protons and neutrons. The protons having positive charge, they strongly repel each other electrically, and the nucleus is held together by the residual strong force. The strong force is the force that binds the quarks together in a hadron. The force is felt a little beyond the radius of the hadrons, given by their de Broglie wavelength. The de Broglie wavelength of a proton is of the order of 10 to the minus 13 centimeter. The residual force is enough to bind the nucleons together in a nucleus, much in the same way the molecules are held together by a residual of the electromagnetic interaction, which is called the London force. The nuclear force decays exponentially and is only felt up to a couple nuclear radii away. If free protons are to fuse, they must come close together by approximately this distance, 10 to the minus 13 centimeter. And that poses a problem, that the electric repulsion by the Coulomb force is proportional to the inverse square of the distance. At 10 to the minus 13 centimeter separation, the energy of the Coulomb repulsion is about 1 mega electron volt. That means that it is to fuse, two protons must overcome the Coulomb potential barrier of about 1 mega electron volt. If they can get closer than this distance, if they can overcome this 1 mega electron volt barrier, they then can come into the deep potential of the strong force. So the Coulomb barrier is the square of the electron charge over radius, and for a radius of about 10 to the minus 13 centimeter, that gives you 1 mega electron volt. The kinetic energy that an atom is going to have at the core of the sun, where the temperature is about 10 to the 7 Kelvin, the typical kinetic energy is going to be the Boltzmann constant times this temperature. And that will give you energies of the order of kilo electron volt. When dealing with this units, it's useful to write the Boltzmann constant in terms of electron volt per Kelvin, which is 8.62 times 10 to the minus 5 electron volt per Kelvin. So the conclusion is that the kinetic energy of protons, even at the core of the sun, is too low to overcome the Coulomb barrier and fuse. You have to overcome a barrier of 1 mega electron volt, but by kinetic energy alone, you only have an energy of about kilo electron volt. It's much, much too low to overcome the potential barrier. Classically, the protons cannot overcome the Coulomb barrier, but they can quantum mechanically tunnel, reach the other side, and fuse. So to know the nuclear reaction rate, we must know the probability of quantum tunneling. You may remember from the luminosity equation that we had dl over dr was equal to 4 pi r square rho times epsilon, where epsilon was the nuclear reaction rate. So let's find this quantity epsilon. The unit given by this equation of this epsilon must be erg per second per gram. That is, it gives you how much power, energy per second, one gets by gram of material. Then if we multiply by the density, we get something that is in units of erg per second per volume. That is the power per unit volume. We can connect this quantity to a reaction rate per unit volume. Let's call it gamma. This unit of gamma is going to be the rate per volume, so 1 over second per volume. So that means that to get rho epsilon, you need to simply multiply gamma by the amount of energy delta E that one gets from a single reaction. That is, rho epsilon must be equal to gamma times delta epsilon of a single nuclear reaction. Combining these ideas, then your nuclear reaction rate must be gamma times the energy of a single reaction over the density. And what should go in the reaction rate gamma? Well, we can have an idea by dimensional analysis. Any reaction must be between two reagents. You have the reagent 1 and the reagent 2. The reagent 1 has number densities n1, and the reagent 2 has number densities n2. Any reaction rate must be proportional to N1 times N2, the number densities of the two reagents. Now, it must also depend on the cross-section of the approaching nuclei. So let's also give a dependency sigma, where sigma is a cross-section that the two reagents combinedly offer to each other. But we have that the unit of gamma is 1/2 over the volume. Whereas this N1, N2 times sigma is going to give you centimeter square over centimeter to the 6th power. So that gives you something of centimeter to the 4th power. So to have this proportionality give you 1/2 over centimeter cube, you are missing here something of dimension centimeter per second, which is the unit of a velocity. So any missing quantities must contribute a unit of centimeter per second to make the dimensionality constant. We are therefore missing a velocity in here. So you can write that the reaction rate is going to be proportional to N1, N2 times sigma times the velocity. Now, what cross-section and what velocity are to be used? Particles, if they are in thermal equilibrium, will have a Maxwell-Boltzmann distribution of velocities. And the cross-section for particles are not their physical radii, but their de Broglie wavelengths, and augmented by the tunneling probabilities. And both of these are function of energy. So we need to rely on statistical averages here. We can substitute the proportionality by inequality if we define the average of these quantities, where this average is a weighted average in energy. And Fe is the probability distribution of energy. That's the Maxwell-Boltzmann. In terms of energy, the Maxwell-Boltzmann is. Thus, we only need to know the reaction cross-section sigma of E to calculate the reaction rates. Now, the reaction cross-section should be the geometrical cross-section, where lambda is the de Broglie wavelength of the nucleus, augmented by the probability of tunneling through the Coulomb barrier. Now, since the de Broglie wavelength is h over p, where p is the momentum, this is equal to h over square root of 2m times the energy, then you have that lambda squared is proportional to 1 over the energy. The cross-section for the reaction rate then is proportional to 1 over energy times the probability of tunneling, which is also a function of the energy. We need now then to know what is this probability of tunneling. That requires a quantum mechanical calculation. It's a simple quantum mechanical calculation though. Let's find out the probability of quantum tunneling.